Okay, the next topic is practical problems on union and intersection. Well, how practical these problems really are, that is debatable, but anyway, here it is. So, U is again a universal set and it has two subsets A and B. We have drawn the Venn diagram as usual. Now, in this diagram, the region represented by these horizontal stripes is for the set A difference B, and the one represented by the vertical stripes, that region is for the set B difference A, and the region having these dots is your A intersection B. Now, while discussing unions and intersections, at one point we mentioned these facts, namely that if you take the union of these three sets, A difference B, A intersection B, and B difference A, then you get A union B, which can clearly be seen from the Venn diagram. Although, again I am repeating, a Venn diagram is not a proof of any set identity. If you really want to prove this, you have to go the usual way. That is, you have to show that this is a subset of that and that is a subset of this by taking arbitrary element, that is, say you take x here, then show that x belongs to that set and so on. Now, I am not going to go with that proof. In fact, I leave that proof to you. Having seen at least two such proofs of, I think, one of the distributive laws, and the other thing that we proved rigorously is, I think, the fact that union of sets is associative. So, having gone through them already, I am fairly confident that you will be able to prove this one also similarly. Another fact is that these three sets form a family of, or a collection of, mutually disjoint sets. In other words, if you take any two of these three sets and take their intersection, that intersection is empty. In other words, any two sets out of these three sets are disjoint, which is what we have written here. And these facts also can be similarly proved. We are here not really interested in proving these facts, but starting from these facts, say these facts are given to us. Now, what can we say from that? Note that because we have three sets, this one, and this one, their union is A union B, and they do not have any mutual intersections that are non-empty. All the intersections are empty. Now, in this situation, if both the sets A and B are finite sets, say, of course, whatever we have said here, whatever we have written here, is true even for infinite sets A and B. Or maybe A is infinite, B is finite, all the possibilities are there. For all such possibilities, these are true. But in particular, if both A and B are finite, then what can we say about these three sets? Obviously, they are also going to be finite. For example, since A is finite, A has only finitely many elements. And A difference B, that means this region, is a subset of A. So, automatically it will also have finitely many elements, maybe less elements than A. So, that is why A difference B is finite. Similarly, finiteness of B implies that B difference A is finite. And what about the intersection? The intersection, well, this in fact is a subset of both A as well as B. So, it's also finite. That means we are looking at three finite sets whose union is A union B. What else is true? There is no intersection, there is no common element between any two of these three finite sets. That is why If we take the number of elements in A difference B, the number of elements in B difference A, and the number of elements in A intersection B, and add them up, we will obviously get the number of elements in A union B. It's like saying something like this. Say you have 3 bags. In one bag you have 2 red balls. In another bag, in this bag, you have 2 red balls. In this middle bag, you have 3 white balls. And in this one, you have, say, 2 blue balls. So what is the total number of balls without considering the colors? 2 plus 3 plus 2. So that means 7. Okay, so that's how, if you add the number of elements in A difference B, A intersection B, and B difference A, you are going to get the number of elements in A union B. That's why we write, hence, N number of elements in A union B is equal to the number of elements in A difference B plus the number of elements in A intersection B plus the number of elements in B difference A. Okay. Now we are going to next consider a similar thing, but only for the set A. Just like we have divided the union of A and B into 3 disjoint parts, so that the sum total of all the parts is the entire set and the parts do not have any common intersection. Just like that, we can also divide only A into 2 parts. One of them is A difference B and the other is A intersection B. That's why we can write also A is equal to A difference B union A intersection B. Okay, let me just give this equation some numbers, say equation 1. Now you combine with this fact, the fact that A difference B and, well, which one? This one, and A intersection B are disjoint. You then again get the fact that the number of elements in A difference B and the number of elements in A intersection B together, if you add them up, you are going to get the number of elements in A. Just like you have got this equation, a smaller version of that similar equation you will get here from this. And you are going to get this in fact. So, the number of elements in A is equal to the number of elements in A difference B plus the number of elements in A intersection B. Let me call it 2. Also, whatever we did with A, we can also do with B similarly, and we can recognize the fact that B is the union of B difference A and A intersection B. And these two sets are also disjoint. So if we sum the number of elements in them, we should get the number of elements in B. So we get a third equation also. This plus this. Now from equations 2 and 3, we can write expressions for this and this. from equations 2 and 3, we are going to get two things. From equation 2, we will get n A difference B equal to n A minus n A intersection B. And from equation 3, we are going to get a similar expression for n B difference A. And n B difference A is equal to NB minus N A intersection B. Next, what we do, we are going to use these expressions in equation 1. That is, we are going to replace N A difference B by this and replace N B difference A by that expression in equation 1. Using these, in equation 1, we get, so the left hand side of course will just be N A union B. Now in its place, we are going to write N A minus N A intersection B. In order to emphasize the fact that you have written this expression for this single term, you can use brackets, okay, square brackets. Similarly for this one, let us not change anything. In fact, the order also in which these terms appear, let us keep that order also intact. After this, we write this. And then we are going to write, in place of n B difference A, we are going to write this. That is n of B minus n of A intersection B. Note that you have now got 3 n A intersection B's, 2 of which are minus and 1 of them is plus. So that means 2 of them will cancel out and we will be left with a minus. That means we are going to get NA plus NB minus NA intersection B. Okay, so we have devised a way of knowing how many elements A union B has in terms of how many elements A has, how many elements B has, and how many their intersection has. And this is a formula. We are going to use this formula to solve some problems. Now this formula, okay, now before we go to a slightly more general version of this formula, let us note one more thing. You note this, the number of elements in A difference B is equal to the number of elements in A minus the number of elements in A intersection B. Or actually, strictly speaking, although it looks different, but this one also is the same formula. The number of elements in B difference A is NB minus NA intersection B. Let us also remember this. This one or this one along with this one. Okay. So these are the things we take away from this discussion. Alright. Now if in place of, next comes a slight generalization of this formula, which is, this one involves 3 sets instead of 2. What if you have A union B union C, then Can you say something about the number of elements in that union? Of course, given that A, B and C are all finite sets. But do not be afraid that we will again have to go through the arguments from scratch. No. We are in fact going to use this formula to find a formula for the three sets case. Let A, B and C be any finite sets. Never forget that this formula only works if both A and B are finite, otherwise it loses meaning. And especially whenever something loses meaning in the sense that it becomes infinite, please do not write some things like this. Say A is infinite, okay? So that A union B is also infinite. In that case, do not write something like this. If B is finite, don't just refrain from writing equations like this which involve infinity, because if you have got a habit of doing this, sooner or later you will make some mistake. One can in fact make these things rigorous, but that is not for us and definitely not for now. Just avoid using infinity in equations like this. Okay, so now what we are going to do, we straight away write the number of elements in A union B union C. At least we know one thing right from the very beginning, namely that because A, B and C are finite, their union is also a finite set. So at least we can talk about the number of elements in the union. That much we know. But now what? You see, the trick here is to view this union. Although there are three sets, we can view this union as a union of two sets, like this. What you do, you consider the sets A union A and B together, thereby obtaining the set A union B, and then you write union C. This is after all itself also a set, no? So we are here looking at the union of two sets, one of which is C and the other is A union B. So on this we can apply that formula. What does the formula say? It says that the number of elements in A union B is the sum of the numbers of elements in A and B minus the number of elements in their intersection. That means this will be, this is one of the sets, plus this is the other set, minus the intersection of these two sets. That is the intersection of A union B and C. Okay. Note now that here you can use the ordinary formula itself, and that gives you NA plus NB minus N A intersection B, and then plus NC minus. Now what will you do here? Here you have to use one of the two distributive laws. That is the only way to go forward. When you do that, it becomes this. You see, A union B intersection C, intersection will go inside. That is, you will have A intersection C and B intersection C. But in the middle, you will have union. A intersection C, let me just write it a bit separately, union B intersection C. In fact, that is why we call it a distributive law. Intersection distributes itself over union. All right. Now, why did we do that, by the way? We did that because we have a formula for the number of elements in a union. And this is now a union of two sets, one of which is A intersection C and the other is B intersection C. So we are again in a position to use that formula here. Okay, now reorganizing this part a little bit more. NA plus NB plus NC minus NA plus NB plus NC minus, let us write this one because we already have it, A intersection B, and minus of this. So it will be, also do not forget that there is a minus. So it's better to do whatever we are going to do within brackets. N of this union this is N of this plus N of this minus N of this intersection this. That means N of A intersection C plus N of B intersection C minus N of A intersection C intersection B intersection C. Okay, now if one carelessly forgets this minus, and then everything will be wrong. I mean, say one writes minus but then just simply goes on writing whatever he likes, then it will be wrong because this minus has its effects on these terms also. Alright, so now what are we getting? NA plus NB plus NC minus NA intersection B minus, let us now multiply this minus by this minus 1. NA intersection C minus N B intersection C, but then this minus and minus become plus N. Now if you intersect A intersection C and B intersection C, you actually get nothing else but simply A intersection B intersection C. So this is the formula for the number of elements in the union of three sets. Now let me once again write the formula for NA union B just below it to notice one thing. In case of two sets, we have this, right? NB minus NA intersection B. And let us now see one pattern. That is the pattern in which terms are appearing in these formulas. In case of two sets, what do you first do? You write the number of elements in the sets and add them up. NA plus NB. Okay. So you have run out of sets. There were only two sets, A and B, and you have written terms for them. But because you have started with plus, the next term will be minus. And then intersections come. So first you consider intersection of any two sets, because here you actually have only two sets, so only one intersection is appearing. Plus, plus, minus, intersection taking two sets at a time. When we get three sets, you do similarly for the single sets NA plus NB plus NC. But then the other terms after that will be minus because we have started with plus. And now there are 3 sets, out of which you next have to take 2 sets and their intersections, all possible intersections. A and B, A and C, B and C. So minus n A intersection B, minus n A intersection C, minus n B intersection C. But after these minuses, again plus will come back. And now you have to take 3 sets out of 3 sets, so there is only one possibility, which is this. Now, following this pattern, if I try to write the similar formula for 4 sets, I should write this. Say there are 4 finite sets A, B, C and D, and I want to find a formula for the number of elements in their union. Then I should write, if I really follow this pattern, I should write this. First I write this individual sets, their numbers of elements and the sum of those numbers, then minus. I next consider intersections taking any 2 sets at a time, all possibilities. I would then have to consider these: A intersection B minus A intersection C, A intersection D, minus. Next comes B. With A I have considered all these. Next with B I am going to consider C and D. And next with C I am going to consider D. And that are all the possibilities. Then after minus, plus comes back. Now this time, out of these 4 sets, we are going to take any 3. So that means 1 will be left out. So you can leave D out and consider A, B and C. Or you can leave C out and consider A, B and D. You can also leave B out and consider A, C and D. And finally, you can leave out A and consider B, C and D. But still more time should be there because we have taken 3 out of 4. So we can still take 4 out of 4, that means all of them. So after plus, again minus will come back. And we will have this. So that is the pattern in which you can write any formula, no matter how many sets you have. But the question remains, is this true? Yes, it is true, and in fact this is the pattern. And the general one also, one can write if one wishes. We are not really going to need this ever in this book, but the case of 3 sets, I think we will need in one of the miscellaneous problems. In solving such problems, we will need. In the exercise set at the end of this section, we are not going to need the 3 sets case. And you can just forget about these things, okay? So next we are going to see some examples which will illustrate uses of these formulas. Let's start with this example. Here we have 2 sets. If X and Y are two sets such that the number of elements in X union Y is 50. The number of elements in X is 28 and the number of elements in Y is 32. What is the number of elements in X intersection Y? So it's simple because we have our formula and out of the 4 terms in that formula 3 are given, so we can calculate the 4th one. Solution, we have this. Nx plus ny minus nx intersection y. So, but we need nx intersection y. So, nx intersection y is equal to nx plus ny minus nx union y. So that means this is 28 plus 32 minus 50. 2 plus 3, 5, so that gets cancelled and you have 8 plus 2, 10. Okay, so there are 10 elements in X intersection Y. Next example, in a school there are 20 teachers. In a school there are 20 teachers who teach mathematics and physics. Okay, so the school will be a very big school. Big school means there will be many standards and there will be teachers for the different standards. And they teach mathematics and physics. Of these, 12 teach mathematics and 4 teach both mathematics and physics. And 4 teach both mathematics and physics. It's understood. There's no need to write everything down. How many teach physics? Okay, while solving such problems, you will have to first of all name the sets. Let the sets of teachers in the school who teach maths and physics B, M and P. Respectively. That means out of these 20 teachers, those teachers who teach mathematics, they form the set M, and those who teach physics, they form the set P. You may notice that I have not written A and B or X and Y, and I have simply chosen to write M and P, taking the first letters of these words, mathematics and physics. That way, we can easily remember which symbol represents what set. Okay, you can always do this and you will never forget. Okay, and as a result, you will never make mistakes also. Now, what are the things we are given? We are given that 20 teachers teach mathematics and physics. Okay, so that means the number of teachers who teach either maths or physics or both is 20. That means the union has size 20. Also, it's given that 12 teach mathematics. That means the number of elements in M is 12 and 4 teach both the subjects. So the number of elements in M intersection P is 4. You should also write this. We are to find the number of physics teachers. We know that N M union P is equal to NM plus NP minus N M intersection P. So you need NP, so NP is equal to N M union P plus NM intersection P minus NM. Minus NM. And you can continue your calculation. You do not stop, okay. From this itself, you continue. So what is NM union P? That is 20. Plus NM intersection P is 4 minus 12. So this is 24 minus 12. This is equal to 12. That means there are 12 teachers who teach physics. And you should in fact write at the end of the solution this in words like this. So the number of teachers in the school who teach physics is 12. Okay, so that's how you should end the solution. But of course, I am not going to write all these things every time. I have just shown how it is to be written for one solution. The rest is left to you. I am going to be very brief with the other examples. Then the next one. In a class of 35 students, This is the most boring part of these problems, writing the problem down. 24 like to play cricket. And 16 like to play football. Also, each student likes to play at least one. Okay. Each student likes to play at least one of the two games. All right. How many students like to play both? It's a question. Okay, so as I said, I'm going to be very brief. I won't write almost anything, and I will just simply say, let the sets of the students who play football, cricket was mentioned first, but it does not matter, be F, and let the students who like to play cricket form the set C. All right. Now, it is given that the total number of students is 35. 24 of them like to play cricket and 16 like to play football. And another very crucial piece of information is also given. Each student likes to play at least one of the two games. Why do we need this line? You see, if you do not have this line, then what is the guarantee that out of these 35 students, there is no student who is, say, not liking either cricket or football? That person doesn't like any of these two games. Maybe there will be someone like that, right? That possibility remains unless you say this. Here it is explicitly mentioned that each student likes to play at least one of the games. So no one is sitting idly, okay, during game time. And that is why the union of F and C covers the set of these 35 students fully, which is why we are able to write this. The number of elements in F union C is 35. Without this line, you are not sure of this. You can only say that this is less than or equal to 35. It may actually be less because there may be some student who likes to play neither football nor cricket. Maybe they like to play tennis or something else. But now because of this we have this. Okay. What else are we given? The cricket fans form the set of 24 students and the football fans form the set of 16 students. How many like to play both the games? That means we need to calculate the number of elements in the intersection. and this is NF plus NC minus NF union C. That means 16 plus 24 minus 35. That is 40 minus 35 equal to 5. So only 5 students like to play both football and cricket. The next one, in a survey of 400 students in a school, something was found. What is it? 100 were listed as taking apple juice, 150 as taking orange juice. As taking apple juice, 150 as taking orange juice. Okay, what else? And 75 were listed as taking both. Okay, how many takes neither apple nor orange juice? Yeah. Neither apple nor orange juice. And this example is going to bring out that point. What happens when you do not have this line? All right. Now, in order to make this, in fact, clearer, we can draw a little Venn diagram for our own understanding. This Venn diagram is not a part of the solution. Okay. You need not draw it. So, let me denote by U the set of all students in the survey. That is 400 students. That means U is our universal set and the number of elements in U is 400. Among these students, 100 were listed as taking apple juice. They like apple juice. And that is this set. Let me call it A for apple. And 150 likes to take orange juice. So let me call that set O for orange. And they are of course both subsets of U, because after all, from all these students only we are considering those two sets. So what else is given? 100 of them like to take apple juice and 150 of them like to take orange juice. But again, in general, there may be intersections, and there is 75 like to take both. So that means A intersection O is 75. All right. Now, after this, after having all these things, it is not said that each of these 400 students like to take either apple juice or orange juice. That is not given. And in fact, instead of that, we have been asked to find how many like neither. So there are students who like to take only apple juice, and there are students who like to take only orange juice, and there are also students who like to take both, but there are also students who like to take neither, and that number we have to find. In other words, we have to find this, the number of elements in the complement of A union O. This is the number we have to find. And this number obviously is the number of elements in U difference the number of minus this. Okay, and for this we have our usual formula. But again, be careful, because there is a minus, let us put a bracket. N of A plus N of O minus N of A intersection O, and then we close the bracket. That is 400 minus 100 plus 150 minus 75. Okay, and what is the final answer? The final answer is 225. Do we really get 225? 250, let me just see. Okay, minus 75. 175 plus 275, 5, 5, 10. Yes. I think I have already said that I cannot do this type of calculations mentally. It is so bad that unless I write like that, I am unable to do it. This is one of my, what you can say, a weakness. But it is what it is. I don't really care. Okay, so 225 students are there who like neither apple juice nor orange juice. And then there is one last one. There are 200 individuals with a skin disorder. Well, I also have a skin disorder, which is why I have to appear like this. There are individuals with a skin disorder. Okay, then what happened? 120 have been exposed to chemical C1. Exposed to chemical C1 means what? Is it like a medicine test, or is it because they got exposed to chemical that they got skin disorder? That is not, I think it's some kind of medicine. Okay, just to see how they react. Maybe, although it's not really necessary for us to know in order to solve this problem. 120 have been exposed to chemical C1, 50 to chemical C2 and 30 to both. Now we have to find three things. Find the number of individuals exposed to. So there are these three parts to the problem. Number one, chemical C1 but not chemical C2. Number two, chemical C2 but not chemical C1. And number three, chemical C1 or chemical C2. Oh, these are questions, right? So for solution, here however, because the chemicals themselves have been named C1 and C2, we will have to name the sets something else. And that means I have to write, otherwise it will become confusing. Let A and B be the sets of individuals who got exposed to chemicals C1 and C2 respectively. So there are 200 individuals with a skin disorder, 120 have been exposed to C1, 50 to C2 and 30 to, okay, so all the things are given. And C2 respectively. Now, so let us start writing all the things. Okay. Actually, this should have been written in the beginning itself. Also, let U be the set of the 200 individuals who have the skin disorder. And now we can write the numbers. So the number of elements in U is 200. Then the number of elements of those people who got exposed to chemical 1 is 120. Those who got exposed to chemical, chemical C2, I said chemical 1 no? Just now, chemical C1, 50. And those who got exposed to both is 30 in number. So in the first one we have to find this. The number of individuals who got exposed to C1 but not C2, that means we have to find the number of elements in A difference B. Now you recall one of the two formulas that we put within boxes. According to the smaller one of them, this is NA minus NA intersection B. Do not carelessly write NA minus NB. Okay, that may not be true. Keep in mind that we have found this only after analyzing all the other formulas and Venn diagram and everything. If you, however, casually simply write NA minus NB, that will be false. That may be true only when B is a subset of A. But to be absolutely sure that what you are writing is correct, you write this itself. Okay, so what is NA? 120. And what is the intersection? This is 30. That means 90. Similarly, how many got exposed to chemical C2 but not C1? That will be NA, NB in difference A. NB difference A is similarly NB minus NA intersection B. So NB is 50. 50 minus 30 is 20. 20 of them got exposed to only C2 but not C1. And in the third one, we have to find the number of people who got exposed to C1 or C2. So that means it's the union. So here we apply your usual formula. Oh, there is, hold on, am I doing it correctly though? Yes, yeah, okay. So that means it is 120 plus 50 minus 30 so it's going to be 140, and that is the answer. Why did I suddenly get somewhat confused? Maybe because of this. This part is unnecessary. I mean, it's there, 200 individuals are there, and something else is said about them, but we never had to use this part of our hypothesis. Our hypothesis includes all these things, right? All these numbers, but this part we did not have to use. Okay, so that's just it. And that completes this section. After this section, as usual, there is a set of exercises, which I am going to upload with the video itself in the community section. And our set theory chapter is almost over, except there are the miscellaneous exercises. So next we will see that. And once those are over, we can move on to the next chapter. So that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.